If you have a capacitor and it's fully charged at 330 volts, how much energy is trapped inside of it? And if you double the distance between the plates, what happens to the energy? The energy stored inside of a capacitor is given with this formula. Potential energy equals 1 over 2 capacitance voltage squared. This is on the pre-cheat sheet in the description and it's derived by integrating the small bits of work that are needed to charge from 0 to Q. Here are some alternative forms because Q is equal to CV. So you can also say PE equals 1 over 2 QV or 1 over 2 times Q2 over C. These are all equivalent. They're all the same thing. You pick whatever form matches the known values in your problem. Let's go through the first example. It's a camera flash. You have 660 microfarads charged at 330 volts. And the amount of energy stored is what we're looking for. The amount of energy stored is given by that formula that we just looked at, which was 1 over 2 capacitance voltage squared. So the capacitance, 660 times 10 to the power of negative 6 to convert it to normal farads times 330 volts squared, giving us 36 joules of potential energy. That's the energy stored inside of a capacitor. What if we try to find the power output that's released in 1 millisecond during this camera flash? Power is equal to energy over time, right? It's the rate at which work is done, or energy in this case, which is 36 divided by the amount of time, which is 1 millisecond. And it gives us 36,000 watts. This is why it can power a flash. It's very, very short duration, but very high power output. What happens if you pull the plates apart? The capacitor is disconnected. So that means the charge stays constant. But if the distance is increasing, that means the capacitor, which relies on distance, decreases. So distance goes up, but capacitance goes down. And since potential energy, or the stored energy, is equal to 1 over 2 times charge squared over capacitance, remember one of the variations, and all of them are in the cheat sheet in the description for free. Since capacitance goes down, Q is constant, and distance goes up, overall, your energy increases when you pull the plates apart. And this makes sense because when you pull them apart, you're doing work. So the energy naturally increases. And here's a quick recap of the molecular explanation. Your positive plate attracts your negative plate, so separating them takes effort, just like pulling a compressed spring takes effort. That's where the work comes from. Where's the energy actually stored? Let's relate it to the electric field between the plates. So here's what we know. Capacitance is permittivity times area over distance, right? Voltage is energy times distance. So potential energy, which was given with this formula, expanded by subbing in these individual equations, gives us potential energy as 1 over 2 capacity times voltage squared. And since area times distance is equal to volume, then that means the density of the energy is 1 over 2 permittivity electric field squared. But the energy is stored inside the electric field itself.